Last night's problem was to find the freezing point for a 2.50 molar solution of NaCl. Okay? So the equation we're going to be working with if we're trying to find the freezing point for a solution, there's actually two equations. The first one we're going to use is this delta T, and then you put a subscript F for freezing, because there's two different kinds of changes in temperature. And that's going to be equal to I, which is the Van't Hoff factor we said yesterday. You want to open that door, please? Thank you. And then the freezing point constant, so we got an F down here for freezing point constant. And then we got M for molality. All right. The other equation we're going to need is, once we find this change in freezing point, okay, then we're going to use this equation where the change in the temperature of freezing is equal to the final temperature minus the initial temperature. Okay? Now, initial temperature is always the freezing temperature of the pure solvent. Initial temperature is always freezing temperature Need your eyes and ears up here, please. Okay. So, in the problem, I gave you this number here. I gave you that number, and yesterday we learned to figure out this number. Our solute is NaCl, and if you take solid NaCl, which is table salt, the white crystal stuff you shake on your steaks and vegetables, and you put it in water, it dissolves. And when an ionic compound dissolves, it breaks up into separate ions, and we get sodium ions and chloride ions. And so the number of particles we get from that breakup is 2. So I equals 2. Now we have everything in this equation. All right, we're ready to plug in everything to that equation to find this number. So delta T sub F for the change of temperature of freezing is equal to 2. The number I gave you for the freezing point constant of water is negative 1.86 degrees C per mole, and then times the concentration in molality. Okay, and I gave you that in the problem yesterday as 2.50 mole. So we just simply put these numbers here over 1, cancel the concentration unit that's the same on the top and bottom, and we're left with degrees C, and when I'm looking for temperature, degrees C works, doesn't it? Alright, so now we're ready to get out the calculators and plug in the numbers. So 2 times, turn it on, 2 times negative 1.86 times 2.50. Okay, negative 9.3 is what the calculator says. The units of measurement I have left are degrees C. Now let's figure out how many significant digits we need. We counted the number of ions here, didn't we? 1, 2. So that's a counting number. We don't use counting numbers when we're figuring out significant digits for multiplication and division. This is a calculated number, and this is a calculated number. Those two numbers we do use. How many significant digits in these numbers? 3 here and 3 here. The 0 is significant because it follows both a decimal place and a non-zero digit. So how many digits do I need in the final answer?
1 more. The 0.
Okay? And so that is the change of temperature of freezing. Okay? Now we're ready to plug that number in here. Okay? We already have initial temperature because the initial temperature is the freezing point of the pure solvent. And I told you in the problem that that number was 0.00 degrees C. So let's plug all that into that equation. We have delta T, that's the change in temperature of freezing, equals temperature final minus temperature initial. We know this number, that's negative 9.30 degrees C. Let's see, we don't know the final temperature, that's what we want to find. And then we know this one because that's always the freezing point of the pure solvent. 0.00 degrees C. Okay? So what I need to do is isolate the unknown. Just like the process we use for gas law problems, we're going to isolate the unknown. When it's an addition or subtraction problem, you have to use addition and subtraction to get rid of your the things you need to get the unknown isolated. So we're going to add 0.00 degrees C to both sides. Okay? Well, when I add 0.00 degrees C, of course this all cancels, and 0 is just 0. So the answer to this question is negative 9.30 degrees C equals the final temperature. Yeah, that's a significant digits error. It's not a lot of points, but you need to learn to do that right. Okay? Okay? All right. What we're going to do now is, now that's the basic equation. All right? That's the basic equation. This and this together make up the two equations. They're pretty simple. You got to kind of memorize the equation. Okay? But prior to learning this equation yesterday, we calculated concentration. And we calculated concentration for 3 different kinds of units. And molality was one of those. So now I'm going to give you a problem where you actually have to calculate the concentration and then plug it into this. Okay? So we've learned how to do this. Now we're going to step it up a little bit by putting together what we learned earlier in the week with what we were learning yesterday about this. Okay? This is a problem for you to practice right now in class, yes. Now I gave you in the problem for homework the freezing point constant for water. What was that?
0.
Yeah, it's negative 1.86. So the freezing point constant for water, this is only for water. It's not for any other solvent. For water, the freezing point constant, negative 1.86 degrees C over molal. Okay? And in last night's problem, I also gave you the freezing temperature for water, which you should already know, really. What was that? 0.00 degrees C. Okay? Well, if your solvent is water, these are always going to be true. If what you're using to dissolve is water, that's the solvent, then these are always going to be true. Hello? Hey. Okay, you want me to send her? Okay, sure. Fine. Okay? All right, so your two equations, remember, delta T, it's a constant that I gave you. Change in temperature of freezing is equal to Van't Hoff factor, which we learned to do already, freezing point constant that I gave you, or freezing point constant for water, and M, which is the molar concentration. I haven't given you molar concentration in this problem. We learned to figure out molar concentration 2 and 3 days ago. Okay? And then once you find the temperature of freezing, that gets plugged into this equation. And this is change in temperature of freezing equals the final temperature. That's the temperature of freezing for the solution minus the initial temperature, which is the temperature of freezing for the pure solvent.
So once you do the first equation, you do the second equation, you get the formula.
Yeah.
That's why I put that right out.
Yeah. Okay. So you should know how to calculate. You should have notes on how to calculate molality. You've got the information you need for calculating molality. Find the molality, plug that in. You know this one already. Figure out I from the formula. Oh, it's not magnesium. I'm sorry. I forgot to put chlorate here. Magnesium chlorate. Magnesium chlorate. Okay? So you have to figure out what the properly balanced formula is to figure out the number of ions you're going to need for I. Okay? Yeah, that's in your test references, and you'll find those chlorate should be on your common ions list.